Okay, so today we'll go over the last of Thermo. I've just opened that door just because it's going to get really hot in here. Alright, so that chart that you have there is the psychrometric chart. So it's to do with humidity in the air. So I'm sure you guys have heard of humidity. It's how much water content is present in the air. Okay. Have you had your lecture on it yet? No. Okay, cool. Well, you'll understand a bit more about it, but I'll go over how to use the psychrometric chart and problems to do with it. Okay, so basically this chart here, on the bottom, on the x-axis, so running along the bottom here is the x-axis, and this is your dry bulb temperature. So when they say dry bulb temperature, it just means the temperature that you would read on your thermometer. Okay, so that's just your normal temperature, what the temperature actually is. And then, so going along the top there, the curved lines, you have WB, which stands for wet bulb. So wet bulb, and basically what that tells you is the greater, the lower the humidity is, the less the wet bulb temperature will be compared to the dry bulb temperature. So it's just an indication of how much humidity is in the air, okay? And it's going to be in relation. So, and you have to remember that the wet bulb temperature, the lines go diagonally. Okay, so you see those diagonal lines on your graph, those are the wet bulb lines. Okay, and then going up on the y-axis, you've got your moisture content. So that's how many grams of water is in the air per kilogram of air. So the grams of water per kilogram of air. Okay, that's the moisture content. All right. So we'll just get into a few examples of how you can use this. So that first question, we've got a dew point temperature inside a car with the windows closed and no air entering. So the significance of the windows being closed and no air entering is that the amount of water inside the car isn't going to change. Okay, so the moisture content, the amount of water in the car is going to remain constant. Okay, and then we're told that the dew point is 14 degrees Celsius, and then we know that the dry bulb temperature is 22 degrees Celsius, so we want to find the relative humidity. So the dew point temperature is the temp at which the relative humidity, RH relative humidity, would be 100%. Okay. All right. So what you need to do here is you need to find the dew point. So dew point is going to be a relative humidity of 100%. So you have your this line here, and so you need to find 14 degrees wet bulb. So you find that line there. So identify that line, and that's going to go across diagonally. Okay, and then On the x-axis, you've been told the dry bulb temperature. So you're going to find 22 degrees Celsius there. And then you're going to see where they intersect. So it's going to be at this point here. Okay. And then you're going to find the relative humidity line, which intersects at that point there. And that's going to be the 60% relative humidity. Okay. All right. And you'll understand a bit more about what this all means later on, but for now I'm just telling you how to solve it. Yep.
So when they say dew point temperature in a question, do we always assume that that is equivalent to the wet bulb temperature? Like that's just the same thing?
Yeah, wet bulb temperature at 100% humidity. Yeah. So when they say dew point, it's the wet bulb temperature at 100% humidity. Okay? Yeah.
Wait, what is it? 60%?
So if you look at your 22, sorry, the dew point, oh, my bad. Yeah, sorry. So because this is dew point, if they said it was wet bulb, you'd go down, you'd follow that diagonal line. But since it's the dew point, you're going to go across horizontally. Sorry, that's my bad. Yeah. So if they say dew point, you're going to find the 100% relative humidity line for the wet bulb temperature, and then you're going to go across horizontally. So my bad for that one. Okay, so next one. In a closed room, again, so that means that the moisture content will stay constant. A dry bulb thermometer reads 20 degrees Celsius, and a wet bulb thermometer reads 15 degrees Celsius. The walls are cooled down until condensation forms on them. What's the wall temperature when this begins? So this time we've been told the wet bulb temperature, so we're going to have to go diagonally, like I did before at the start. So you've got, you're going to find 20 degrees on the bottom, the dry bulb temperature, and then you're going to find going to find 15 degrees wet bulb, and that's going to go across diagonally. So because they've told you the wet bulb temperature, you're going to follow that diagonally. You're going to find that intersection point. Okay. So that's your intersection point. And so this level here, the height of this tells us how much moisture content is in the room. So what's happening is the dry bulb temperature is decreasing, so we're going to move to the left. But remember that the moisture content inside the room isn't changing, so we're not going to change the height. So we're just going to move left horizontally and until we get to 100% relative humidity. And if you do that, this point here, where it intersects with the 100% relative humidity line, is going to be your dew point temperature. So that's going to be 12. So that should be 12 wet bulb. Okay. Number 3. We have a meeting room kept at a constant dry bulb temperature of 18 degrees Celsius by an air conditioner. The room contains 180 kilograms of dry air, and at the start of a long meeting has a relative humidity of 60%. Over the course of the meeting, the relative humidity of the room increases to 100%, but the dry bulb temperature doesn't change. So how much water vapor is added to the air during this meeting? So you're going to find 18 on the x-axis, and then you're going to find that 60% relative humidity line, and you're going to see where it intersects. Okay, and so if you follow that across horizontally to the right, you're going to find this is the initial moisture content. So moisture content, and that's going to be 8 grams per kilogram. Okay, so this is your initial moisture content. Okay, and then what's happening is that you're going to have your 100% relative humidity line. So the moisture content of the room is going to increase while the dry bulb temperature doesn't change. So we're going to keep going vertically until we meet that 100% relative humidity line. So now we're here, and then we're going to move across to the right to find out what our new moisture content is. Okay, and that's going to be 13. So that's our final moisture content. Okay, so our change in moisture content is going to be 5 grams per kilogram. So what that means is that for every kilogram of air, we've added 5 grams of water. Okay, so then we want to find out the total amount of water that's been added to the air. Okay, and we know that there's 180 kilograms of air. So you're just going to multiply 5 grams by 180, because there's 180 kilograms of air. And that should give you 900 grams of water that's been added. Okay? Sweet. And then number 4, a room contains air and water vapor at a dry bulb temperature of 20 degrees Celsius and a wet bulb temp of 18 degrees Celsius. What's the dew point temperature in the room? So you're going to find 20 dry bulb, and you're going to find 18 wet bulb. Okay, so you're going to find the point where they intersect. So they're going to intersect at this point here. And you want to find the dew point temperature. So remember, when you want the dew point temperature, you're going to move across horizontally for dew point. So you're going to go this way. And where it hits the 100%, so this will be the 100% relative humidity line. At that point there will be your dew point temperature. So whatever the, so that will be, that should be 17 wet bulb at that point there. Okay? So your answer is going to be 17. Okay. Cool. So number 5, we've got a marathon runner losing heat at a rate of 500 watts. So remember that watts is joules per second, the amount of energy they're using per second. And during the course of the 3 hours it takes to complete the marathon, she does mechanical work with an efficiency of 5%. Assuming that she does not ingest any food during the race, how much stored energy has the runner used up over the course of the race? And we want that in megajoules. Okay, so I'll just explain efficiency. Basically, whenever you're doing anything, or whenever you're trying to run or walk or lift weights, not all of the energy that you use is actually converted into work. Only some of it is. Most of it's actually wasted as heat. So your net metabolic energy so this is the energy that your metabolism uses. So how much energy that your body burns up, it can turn into work, right? So that's you actually moving or performing some kind of mechanical task, or it can turn into heat. So in Physics 191, if you have energy, it can only become work or it can only become heat, all right? So that means that, and what efficiency tells you, efficiency tells you how much of your energy is turned into work. So the higher that your efficiency is, the more work you're going to produce for the same amount of energy that you use. So the equation for that is work over the total energy that you use, or your net metabolic energy. Okay, so we're told that her efficiency is 5%. So that means that she's 5% of her energy is turning into work, and that means that 95% of her energy is turning into heat. Okay? So we're told that this heat is 500 watts, right? So she's producing heat at a rate of 500 watts. So we need to find out the total amount of energy that she's been using. So to do that, since we know that heat is 95% of the total, to find out the total, we'll just divide the amount of heat, which is 500 watts, divided by 95%, which is 0.95. And that will be 526.3161 watts. So that's the total amount of energy that she's using. Right? So that means that her work is 26 watts. And so that's the amount of energy that she's using per second, how much energy she's burning up. And since she's doing that for 3 hours, her total energy over the 3 hours is going to be equal to power multiplied by time. So power is 526.316 times 3 hours. So in seconds, that's going to be 3 times 3,600. And that will be 5,684,210 joules, which is in megajoules, that's going to be 5.7 megajoules. Okay. Oh man, I'm sweating so much. So number 6, a person wakes and eats 900 grams of food for breakfast, which has an average energy content of 1.8 megajoules per kilogram, and then goes for a 30-minute run in which they do 1.3 megajoules of work with an average efficiency of 4%. The person's body temperature remains constant throughout this process. So that sentence there, the person's body temperature remains constant throughout this process. What that means is that they're losing heat at the same rate as they're producing heat. Okay? Because if you were producing more heat than the rate at which you were losing heat, then your body temperature would increase, right? So that means that the rate at which they're losing heat is equal to the rate at which they're producing heat. So which one of the following statements is false? So we'll go through these one by one. Option A, the net metabolic energy required for the run was 32.5 megajoules. So remember, net metabolic energy is the amount of energy that the body burnt up in total. So what we've been told concerning the run is that for the run, work equals 1.3 megajoules, and the efficiency was equal to 4%. Okay, so that means that work was 4% of the total. So in order to find the total, it's going to be 1.3 divided by 0.04, or 4%. So then the total is going to be 32.5 megajoules. Okay, so we can see that option A is true. All right. Option B, the person did work. The person did work at a rate of 722 watts while they were running. So power is equal to energy divided by time. The total energy that they used was 32.5. Oh, sorry, this is work. So the amount of work they did was 1.3 megajoules. So 1.3 times 10 to the 6th divided by 30 minutes. So we have to convert that into seconds. 30 times 60. And that will be 722. Okay, so option B is true. All right, and then option C, The person ingested 1.62 megajoules of energy for breakfast. So that's just, they ate 0.9 kilograms of food, and for each kilogram there's 1.8 megajoules of energy. So that's just 0.9 times 1.8, which equals 1.62. So option C is true as well. And then option D, the person lost 1.3 megajoules of heat over the course of the run. So we said before that the total, so we know that they did, on their run, they did 1.3 megajoules of work, and we know that the total energy that they used was 32.5 megajoules. So then how much heat must they have produced over the run? Yep, 31.2. So that means heat would have been 31.2. Because remember that energy can only be turned into work or heat. So the remainder of that total must have come from heat. So D is going to be false. Okay. And then E is true. All right. Any questions about that? Cool. Number 7, you take your dog out for a morning run. Your dog does mechanical work at a rate of 50 watts with an efficiency of 6%. At what rate must your dog lose heat in order to maintain a constant body temperature? So in order to maintain a constant body temperature, it has to lose heat at the same rate as it's producing heat. So we can calculate the rate at which it's producing energy, at which it's producing heat, because we know that, because we know the efficiency. So what we can do is we can calculate the total amount of energy that it's going to be using. So work is equal to 50 watts and efficiency is 6%. So the total is going to be 50 divided by 6%, which is 0.06, and that will give you 833.3 watts. Okay, so that's the total energy being used per second. And remember that anything, it's only work or heat. So the amount of heat being produced must be 833 minus 50, which is going to be 783 watts. And it's going to be option D, which is 780. Okay? All right. Number 8, in a particular 24-hour period, a migratory bird does 0.3 megajoules of work and it loses 2.7 megajoules of heat to the environment. Assuming that the bird remains at a constant temperature, with what average efficiency did the bird do work? So we're looking for the efficiency here. Efficiency is equal to work divided by the total. Okay, so we're told that the amount of work is 0.3 megajoules. And what's the total going to be? 3? Yep. So it's going to be work plus heat right? So that's going to be 3 megajoules. So that's going to be 0.1. So 0.1 as a percentage is going to be 10%. Okay. Okay. Number 9. So this one's about, the next 3 questions are about heat transfer. And you might have trouble understanding it because it's quite a new concept. But I'll do my best to explain it. But you'll just need a bit of time to try and understand it all and get familiar with it. So we've got a patient lying in bed, completely covered by a 10 millimeter thick blanket. So we've got the thickness of the blanket, and above the blanket the air is still, and the convective heat transfer coefficient in still air is approximately 3 watts per meter squared per Kelvin. The patient's skin temperature is stable at 36 degrees Celsius, and the air in the hospital is 24 degrees Celsius. What's the rate at which the patient loses heat due to convection and conduction over 1 square meter in watts? And then we're also told about the thermal conductivity of the blanket, which is 0.03 watts per meter per Kelvin. Okay, so we'll go through that again from the start. Patient lying in his bed is completely covered by a 10 millimeter thick blanket. That value there is D. So the thickness of the blanket is D, and that's 0.01 meters, 10 times 10 to the negative 3. Okay, you can write it as 0.01 meters, or you could write it as 10 times 10 to the negative 3. And then the convective heat transfer coefficient in still air is approximately 3 watts per meter squared per Kelvin. So that's H. Whenever you have heat transfer coefficient, that is H. And that's for, we're going to write subscript convection. And that's going to be 3 watts per meter squared per Kelvin. Okay, and then the next sentence, the patient's skin temperature is 36 degrees and the air is 24 degrees. So that's delta T, our difference in temperature, and that's going to be 12 degrees Celsius. And then, so that last sentence there, what we're looking for is we're looking for the rate of heat transfer. So the amount of heat being transferred, Q, over time per second. Okay, so that's what we're looking for. And we're also told about the thermal conductivity. So thermal conductivity is K. So K is equal to 0.03 watts per meter per Kelvin. Okay, so you've got these variables. So first of all, what you need to do is you need to find we've got the H of convection. We need to find the H of conduction, the heat transfer coefficient of conduction. So H for, I'll just write in a different color now. So the H of conduction is equal to K divided by D. Okay, so K is going to be 0.03 and D is 0.01, and that will be 3 watts per meter squared per Kelvin. Okay, so I mentioned it last week, but conduction is the transfer of heat through touch. So this blanket is touching the person, so heat's going to be transferred through conduction through the blanket and lost to the air. And convection is due to air or the movement of fluid. Okay. So we have the H of conduction and the H of convection. And so now we need to find the H total, which is going to be H of conduction to the power of -1 plus the H of convection to the power of -1, and all of that to the power of -1. Okay, so that's H of conduction is 3 to the -1 plus convection is also 3 to the -1. So all of that to the -1. So H total is equal to 1.5. Okay. All right. So now we have the H total, which is what we need. So the rate of heat transfer, delta Q over T, is equal to H total times the surface area times the difference in temperature. Okay, so that's 1.5 times the surface area, which is 1 meter, 1 square meter. So times 1 times our difference in temperature, which is 12. So that's going to be 18 watts. Okay, so what the heat transfer coefficient is, it's telling you how much heat is going to be transferred through that material. And the higher that the H is, the greater the heat transfer is. And the reason that we have the thickness of the material in there is that, so as we can see that the heat transfer coefficient of conduction is inversely proportional to the thickness of the material. So as the thickness of the material increases, the surface heat transfer coefficient is going to decrease, right? Because if something's thicker, it's going to let less heat through, right? So the thicker that a material is, the less it's going to let heat pass through it. Okay. So number 10, a student stands on a cold mountaintop. He's wearing a layer of clothes which is 5 millimeters thick. So that's D. So D is equal to 5 millimeters, and we have to turn that into meters. So that's either 5 times 10 to the -3 or 0.005 meters. We have a coefficient of thermal conductivity, so that's K, which is equal to 0.01. And the air is quite still, giving a surface heat transfer coefficient of 4 watts per meter squared per Kelvin. So H of surface is equal to 4 watts per meter squared per Kelvin. Okay. And the clothed surface area, which is exposed to cold air, is 1.5 meters squared. So our area is going to be 1.5 meters squared. And the outer surface of the student's clothing, the outer surface of the student's skin beneath the clothing is 35 degrees, while the temperature of the surrounding air is negative 10 degrees. So we need to find the difference in temperature. So that'd be 45 degrees. So we have a temperature difference of 45 degrees Celsius. And remember that if we're talking about delta T, we don't need to convert it into Kelvin, right? And we're after the rate of heat transfer, which is delta Q over T. So we're going to have to do the same thing as last time. We're going to have to find the H of conduction. So H of conduction is equal to K over D. So K is 0.01 and D is 0.005. So that's going to be 2. So that's our H of conduction. And then we need to find the H total. So H total is equal to H of conduction to the power of -1 plus the H of surface to the power of -1, and all of that to the power of -1. So that's going to be 2 to the power of -1 plus 4 to the -1 to the power of -1. And that's going to be 1.3333. Okay, so that's your H total. And now we can plug that into our rate of heat transfer equation. So delta Q over T is equal to H total multiplied by the surface area multiplied by the difference in temperature. So that's 1.3333 times 1.5 times 45, which is going to be 90 watts. Okay. All right. So now we're going to have our last one, number 11. A man's wearing a wetsuit and he's submerged, stationary in a lake which has a water temperature of 12 degrees Celsius. The wetsuit is made of 5 millimeter thick rubber. So that's going to be D. So D is equal to 0.005 meters. And then we have a surface area of 1.4 meters squared. And the inside surface of the wetsuit is at a temperature of 25 degrees Celsius. So in our first sentence, we were told that the water temperature is 12 degrees. So our difference in temperature, delta T, is going to be 13 degrees Celsius. And the thermal conductivity of rubber, so thermal conductivity is K. So K is equal to 0.05. And we want to find the rate of heat transfer, delta Q over T. Okay. So here we don't have to worry about convection or the surface. So this one's a little bit simpler. So I should have put this one first actually, but so we need to find H of conduction. So H of conduction is equal to K over D. And so K was 0.05 and D is 0.005, which is 10. All right, and then delta Q over T is equal to H total times area times delta T. So that's 10 times 1.4 times 13, which will be 182 watts. Okay. All right, so that's it. I'll start the advanced tutorial at 8:30. Okay. So in 10 minutes. All right. Thank you. Yep.